We've been discussing single displacement reactions in lecture, so today we're going to do an experiment using single displacement reactions, and our goal is going to be to rank various elements, both metals and nonmetals, in terms of their reactivity compared to one another. In part A of the lab, we're going to be looking at 5 different metals. We have magnesium, zinc, silver, copper, and iron. And we have solutions of compounds of each of those metals, and we'll be carrying out a series of reactions, and in each case we'll be determining which of those metals is more reactive. So in each reaction there'll be a winner and a loser essentially, and we're going to rank the metals like one would rank sports teams. In the second part of the experiment we're going to be looking at nonmetals. So we have bleach, which is our source of chlorine, and then we have bromine and iodine. So we're looking at 3 of the elements from group 17. So we'll be carrying out a reaction between chlorine and bromine, chlorine and iodine, and bromine and iodine, and then we will rank those 3 elements. Now this is probably the most complicated experiment of the semester in terms of analyzing the data and answering the questions. I've prepared a pretty thorough pre-lab video, so after our brief introduction here, make sure you watch that video, and then we'll head on over into the lab, carry out the chemical reactions for both parts A and B, and then you can use that information to answer the questions at the end of the experiment. We just finished an overview of what we're going to be doing in experiment 9 today. And we've talked in lecture quite a bit about the nature of single displacement reactions. Essentially, a single displacement reaction involves the reaction between an element and a chemical compound. So element A can either be a metal or a nonmetal, and BC represents most commonly an ionic compound, but it can also represent an acid. What we're trying to measure today is something called the activity of an element. Activity is basically the same as reactivity. So in terms of metals and nonmetals, they each want to either gain or lose electrons. So their activity is simply a measure of how much they want to do that. Now, of course, metals and nonmetals don't like to do the same thing in chemical reactions. It's the nature of metals to want to lose electrons. In order to get an octet, it's a shorter path, essentially, for a metal to lose electrons. So in terms of activity, whatever metal most wants to lose electrons, that is the most active metal. Nonmetals, on the other hand, want to gain electrons. Being on the right side of the periodic table, it's a shorter path to an octet for nonmetals to gain electrons. So in terms of nonmetals, whichever one of them most wants to gain electrons, that will be the most active nonmetal. In the first part of the experiment, we're going to be looking at the activities of metals. So you're going to be looking at 6 elements and ranking them in order of their activity. So to do that, we're going to carry out a series of chemical reactions. So before we get into the actual reactions from the lab, let's take a look at a couple of hypothetical examples here. So this is the reaction between nickel and copper. Nickel and copper are both metals, which means they both want to lose electrons, but they can't both do that. Whenever 2 metals react with each other, one of them is going to be forced to gain electrons. So whichever one is able to lose electrons to do what metals want to do, that's the one that will be the more active of the 2. So to determine what's happening, let's take a look at the charges on the elements, just like we did back again in chapter 9. Because to lose electrons means an element is oxidized. So for metals, being oxidized is a good thing. They want to lose electrons. The nickel, its charge went from 0 to positive 2. So an increase in charge, as we learned back in chapter 9, means the element was oxidized. So in this particular reaction, nickel was oxidized, and that's what nickel wants to do. If we look at the charges on the copper, it went from +2 to 0. So the charges on the copper decreased, and that means that the copper was reduced. So in this particular case, since the nickel was oxidized, it's the one that got to lose electrons, that means that nickel is more active than copper. So in this particular competition, nickel beat copper. Now let's take a look at a second reaction. This time we'll look at the reaction between lead and nickel. So the first time we did nickel versus copper. Now we'll do lead versus nickel. If we look at the charges, the lead's charge went from 0 to +2. So an increase in charge means that the lead was oxidized. Nickel's charge went from +2 to 0. A decrease in charge means that the nickel was reduced. So if lead was oxidized and nickel was reduced, then that means in this particular competition, lead was more active than nickel, or lead beat nickel. Now we can put these two results together. They both have nickel in common. So if lead beat nickel and nickel beat copper, we can come up with a series here of activities that shows that lead is more active than nickel and nickel is more active than copper. You're going to do this same thing for the 6 elements in Part A. You're going to do a series of 7 reactions, and using those results, you'll come up with an overall ranking for your 6 elements. Now, in order to determine which element is more or less active, we're assuming that the reaction takes place. So when I write the reaction like this, you're assuming that it will actually react, and the nickel will indeed trade places with copper. And if it did so, we were able to determine that the nickel was indeed more active than the copper. But what would have happened if we had run the reaction in the reverse direction? What if we took a piece of copper and reacted it with nickel chloride to see if we could produce nickel and copper chloride? Would you expect that reaction to happen? The answer is no. Reactions can't go both directions spontaneously. So if nickel wants to react with copper to form copper and nickel chloride, then nickel chloride and copper do not want to go in the reverse direction. The fact that this reaction happens means that it's the downhill direction. If we were carrying this reaction out, it would be going uphill, and it's not going to happen spontaneously. So if you mixed these two things together, we would find that there's no reaction. So can you learn anything from a reaction that doesn't happen? And this is important because of the 7 reactions that you're doing for Part A, 3 of them are actually not going to take place. You're going to mix them together and nothing will occur. So this is the easy thing you can do. We look at this reaction, and initially we assume, okay, this is going to happen. And so we analyze it, we look at the charges, and we say, according to this reaction, copper is oxidized and nickel was reduced, so we would rank copper more active than nickel. But then we do the reaction and say, oh gosh, that reaction did not happen. What that means is the reaction really wants to go in the opposite direction. And if it were to go in the opposite direction, it would simply reverse these two, and we'd end up with our original conclusion of nickel being more active than copper. So when you're doing the reactions for Part A, assume initially that all 7 reactions will happen, and go through the analysis just like we did here, and in each case identify the more and less active element. But then for the 3 in which there was no reaction, simply reverse your conclusion when you fill out the table of information, which I'll show you in a few minutes. These are the 6 elements that you're going to be investigating in Part A of the reaction. 5 of them are metals, the copper, zinc, iron, magnesium, and silver, but we're also using hydrogen as one of our elements. Now, hydrogen is not a metal, but what it has in common with metals is it forms a positive ion. So a hydrogen ion and a metal can trade places just like two metals can do. So these are the 7 reactions that you're going to be carrying out. Now, you won't actually be doing that since we're not on campus right now. So I've done each of these 7 reactions and made a video of each one, and those videos will follow this introduction to the lab. So you're going to carry out each of these 7, and remember, I mentioned earlier that only 4 of them are actually going to react and 3 of them will not. So you want to make sure that you find the correct 4, that you identify the correct 4 that do react and those 3 that don't. And once you've done the lab, you are welcome to check with me and make sure you have everything filled out correctly in the subsequent table. Now, once you've done the reactions, before you can identify the more and less active element, you need to complete the 7 chemical reactions. So you're going to want to take each of these 7 reactions and do what we did in our example a little while ago. Figure out the products, put in the charges, and then figure out who was oxidized and who was reduced. For each of the 7, whichever element was oxidized, that's the one that's more active. However, don't forget, for whichever 3 of these don't react, you simply want to reverse that conclusion when you fill out your table. So once you've written all 7 out, determine who's oxidized and reduced, before you fill out that table, make sure that you reverse the 3. So 4 of these are going to be exactly as you observed in the reaction. The other 3, you're going to have to reverse those results. Now, once we've got these results, we can work on the questions. So question 2 is asking you to rank those 6 elements from the least active to the most active. So you're going to do what we did in our practice example with the nickel and the lead and the copper. You're going to sort of merge together the results of those reactions and come up with an overall listing from the least active element to the most active. And then the last question that deals with part A is question number 3. Now, if you remember in our example, we had 3 elements, copper, nickel, and lead. And to rank them, we had to do 2 reactions. If we want to rank 6 elements, we only need 5 reactions or 5 experiments to do that. So the fact that we did 7 means that 2 of those reactions were unnecessary. They weren't wrong, they simply confirmed what we had figured out from the previous 5 reactions. So they're sort of just confirmatory. So your job in question 3 is to figure out which of the 5 were absolutely necessary to do your reactions and which of the 2 were simply extra reactions that we used to confirm things. In part B of the experiment, we're going to be taking a look at the activities of nonmetals. In particular, we're going to be looking at elements in group 17, chlorine, bromine, and iodine. So let's start out with a practice example here. This will be the reaction of oxygen and nickel chloride. So in order to determine who's oxidized or reduced in the reaction, we need to look at the charges of each of the elements. So elements are always neutral to begin with, so oxygen and chlorine both have a charge of 0. Chloride ions are -1. Oxide ions are -2. So the chlorine, in this case, went from a charge of -1 to 0. That's an increase in the charge. And an increase in charge means that it must have been oxidized, so the chloride ion was oxidized in this reaction. Oxygen's charge went from 0 to -2. A decrease in charge means that the oxygen was reduced. Now, remember, for nonmetals, being reduced is their goal. So whichever element is reduced or gains electrons, that's going to be the more active element in that particular reaction. So in this case, we would rank oxygen as being more active than chlorine. All right, let's take a look at the actual reactions we're going to be doing in part B. So there'll be 3 of them. the first reaction is going to be chlorine versus bromine or bromide ions. The second reaction will be chlorine versus iodine. And the third reaction will be bromine versus iodine. Now, in order to determine if these reactions occur, we're going to be looking at color changes. As you'll see in some of the videos that I have for you, chlorine, bromine, and iodine have very different colors. Chlorine is fairly colorless, bromine is a nice orange color, and iodine is a nice purple or violet color. So we're going to expect to see color changes in the reactions. For example, if this first reaction were to happen, the chlorine would trade places with bromine, and the appearance of bromine should give us a nice orange color. If the second reaction occurred, the colorless chlorine would be replaced by purple iodine, and we would see a lovely purple color appear. So we're going to use those colors as indicators of a chemical reaction taking place. Now, in order for you guys to know what to look for, we're going to first prepare 3 test tubes that just have chlorine, bromine, and iodine in them. And you'll see in the videos in a few minutes how this is set up. We're going to put some water in each of 3 test tubes, and then we'll add to the first test tube some chlorine, second one some bromine, and the third one some iodine. And then we're going to put on top of the water a layer of hexane. Hexane is sort of like gasoline. It doesn't dissolve in water, but chlorine, bromine, and iodine love to dissolve in hexane, and when they do, their colors become very bright. So the hexane is there just as a color enhancer. It's just to make the colors look real pretty. So we're going to have those 3 test tubes as references, so when we do the reactions, you'll know if you see one of those colors appear, you'll know which element was produced in that reaction. Now, once you've done the reactions, your job is to figure out who's the more and less active element in each of these reactions. And to do that, you're going to want to complete these 3 reactions. So even though there wasn't a specific question in the lab, you're going to want to write these reactions out just like we did in Part A, label the charges, and figure out who was oxidized and who was reduced. And then when you fill in the table between chlorine versus bromine, chlorine versus iodine, and bromine versus iodine, you're going to want to list the one that's more active and the one that's less active, keeping in mind that the more active element in Part B will be whichever one is reduced. It's the opposite of what we had in Part A. Question number 4 in the lab simply asks you to rank the 3 elements, the chlorine, bromine, and iodine. And you'll do that just like you did in Part A. You'll look at the results of those reactions and see who was more active than whom in each case, and come up with an overall ranking from the least active of the 3 to the most. And then finally, question number 5 is a hypothetical question. We didn't actually use any fluorine in our reaction because fluorine is a very dangerous element. So I'd like you to try to determine what you think would happen if we used sodium fluoride in a reaction with chlorine. And I'll talk in just a moment here about how you can reason out. Even if you don't do a reaction, it is possible in many cases to predict what's going to happen in one of these reactions. As I mentioned a moment ago, it is often possible to predict the activities of elements without actually doing a chemical reaction. And we can do that by looking at their position on the periodic table. There's a trend on the periodic table as you go from left to right across a period on the table. The desire or ability of an element to gain electrons increases. So the farther you go to the right, the more elements want to gain electrons, or the more they want to become reduced. There's also a trend as you go from the bottom to the top of a group. In any group, as you go up the group, the desire or ability to take electrons also increases. So the higher you are in a group, the more you want to gain electrons. The farther you are to the right, the more you want to gain electrons. And that means that fluorine is the most powerful element on the periodic table. It wants to gain electrons more than any other element. We ignore the elements in group 18 because, of course, they don't want to gain or lose electrons at all. So fluorine is the most active nonmetal on the periodic table. It wants to gain electrons more than any other element. Now, which element do you suppose is the most active metal on the periodic table? Which metal wants to lose electrons more than any other? And the answer, of course, would have to be francium. It's in the opposite corner. So if going to the right and up makes you more likely to gain electrons, and going to the bottom and left makes you more likely to lose electrons. Now, this trend really only works in the S block and the P block. So if the elements are in the D block, there's really no good way to compare them. But if you're in the S and the P block, it's easy to make a comparison. For example, suppose we did a reaction between magnesium and aluminum. They're both metals, which means they both want to lose electrons, but which one's going to want to lose them more? The answer, of course, is magnesium, because magnesium is farther to the left than aluminum, and that means it has a stronger desire to lose electrons. So we would predict that magnesium would be more active than aluminum, and if you did the reaction in the lab, that would be absolutely correct. If we were comparing, say, phosphorus and oxygen, they're both nonmetals, so which one would want to gain electrons more? Well, oxygen is farther to the right and farther up, which means oxygen is definitely going to be stronger. It's going to want electrons more than phosphorus, so we would predict that oxygen would be the more active nonmetal between that pair. And again, if you did an experiment in the lab, that would absolutely turn out to be the case. In the D block, unfortunately, we can't make those kind of predictions. If we tried, for example, if we looked at nickel and copper and said, okay, which of these two wants to lose electrons more and be the more active element, we would predict that the answer would be nickel, because nickel is to the left of copper. Turns out that's actually true. If you do it in the lab, that's what you will notice. But then let's take a look at copper and zinc. Again, based on that trend, we would expect copper to be more active, that copper would want to lose because it's to the left of zinc. Turns out in reality, the opposite is true. Zinc is actually more active than copper. Nickel's more active than copper. There's no trend there. So with elements in the D block, you simply have to do the experiment. But in the S and the P block, it's possible to simply look at their position. So when you do question number 5 in the lab and you're looking at that reaction between chlorine and fluorine, you should be able to make a prediction about what's going to happen based on their relative position on the periodic table. I know that was a pretty involved pre-lab introduction to our experiment, and it is a rather complicated topic. So now it's time to actually carry out the experiment. I will be conducting each of the reactions in part A and B, and I will attach videos of each of those, and then I want you to record your observations in the tables, and then use that information to answer the questions at the end of the lab. This is our first reaction for part A. First, let's add a couple of strips of copper to our test tube. And then we'll add to that some of our silver nitrate solution. And now let's observe what happens. You can see that the copper is beginning to darken pretty rapidly, so clearly a reaction is taking place between the copper and the silver. Here's a close-up view of the copper and the silver. Our next reaction is between zinc and magnesium nitrate. So let's go ahead and add a piece of zinc to our test tube, and then we'll add some of the magnesium nitrate solution. And now let's watch and observe what happens. Several minutes have passed, and it doesn't appear that any reaction is taking place between the magnesium and the zinc. Here is a close-up view of the zinc. Our next reaction will be between concentrated hydrochloric acid and iron. So let's add a piece of iron to our test tube. And then we'll add some hydrochloric acid. And it appears a reaction is beginning to take place, so let's zoom in and see if we can get a better look. Now that we've zoomed in, it's easy to see that a reaction is taking place. We're seeing the solution becoming more yellow and a lot of bubbles forming on the surface of the metal. This is the reaction between zinc nitrate and iron. So let's add a piece of iron to the test tube. And then we'll add some of our zinc nitrate solution. And now let's watch and observe what happens. It's been a few minutes, and there doesn't seem to be any change occurring in either the solution or on the surface of the piece of iron. And here's a close-up of the piece of iron. The next reaction will be between copper nitrate and zinc. So let's add a piece of zinc to our test tube. And now we'll go ahead and add some of the copper nitrate solution. And now let's wait and watch and see what happens. It's been about a minute now, and we can see that the piece of zinc that's submerged in the solution is becoming quite dark. So clearly there's a reaction taking place. Why don't we go ahead and zoom in now for a better look. Up close, it's very clear that a reaction is taking place. The part of the zinc that's immersed in the solution has become quite dark in color. Our sixth reaction will be between magnesium and copper nitrate. So let's add a few strips of magnesium, and then we'll go ahead and add some of our copper nitrate solution. And now let's watch and see what happens. It looks like the magnesium is beginning to darken. So let's go ahead and zoom in a little bit and see if we can get a better look. Up close, it's very clear a substantial reaction is taking place. Those little hair-like growths on the surface of the magnesium are actually crystals of copper metal. Our final reaction in part A will be between sulfuric acid and copper. So let's add a couple of strips of copper to our test tube. And then we'll add to that some sulfuric acid. And now let's watch and see what happens. It's been several minutes now, and there aren't any obvious signs of reaction, so why don't we zoom in a little bit to get a closer look. Up close, it's obvious that the copper is totally unchanged, so clearly there's no reaction in this case. All right, the first thing we're going to do in part B is to prepare some test tubes that have chlorine, bromine, and iodine in them so you can see what the colors ought to look like. So we'll start out by putting some deionized water into the first test tube. Then we'll add a few drops of chlorine in the form of bleach. Bleach isn't really chlorine, but it contains chlorine, so we'll put a few drops of bleach in there. And to activate the bleach, to get it to release its chlorine, we're going to add 1 drop of hydrochloric acid. So now the chlorine is being released into the water. We can swirl that around. So far it doesn't look like anything is happening. Now to make the colors more brilliant, we're going to add a layer of hexane to the top of the water layer. I'll pull the test tube out so you can see there's that little layer of hexane on the top. I'm going to mix that around, and any chlorine that's in the test tube should rise to the top. And since chlorine is fairly colorless, you can see that top layer has very little color to it. All right, I've already added some water to the next 2 test tubes, one that we're going to test bromine and one that we'll take a look at iodine. So let's take the second test tube. I put some water in there, and we'll add some bromine to that one. And then to the top of that, we'll add some hexane. Make a nice layer like we did in the previous one. And then I'm going to mix that around a little bit. So I'm going to swirl this liquid around. And you can see that the hexane layer is getting nice and orange colored. So that orange color up in the top there, that tells us that there's a bromine in that test tube. And then for our third one, we're going to add some iodine to it. And then we will add that hexane layer on that one as well. And we'll swirl that one around. Oh, and if you look real carefully there, you can see now we have a lovely purple color on the top. So the chlorine gives us fairly colorless liquid on the top. The bromine is orange, and the iodine gives us this lovely purple. We're going to use those as indicators when we do our reactions to see whether chlorine, bromine, or iodine are produced in the reaction. Now our first reaction is going to be between potassium bromide and chlorine. So we're going to add some potassium bromide to our test tube. And then we're going to add a couple of drops of bleach. That will be our source of chlorine here. Put a few drops in there. And then we're going to add 1 drop of hydrochloric acid to sort of speed up the reaction. Otherwise it'll take a long time before it happens. And then we'll mix this stuff around. And all of a sudden, oh, look at that. We're seeing an orange color appearing there. So let's add some hexane to the top of this so we can better see that orange color, because if it's orange, it ought to be bromine, of course. So I'm going to take the test tube out for just a moment and get it all nicely mixed up so you can see what the bromine looks like. And as you can see, we've got a nice orange layer on the top. So that color change tells us a reaction did occur, and apparently the reaction produced bromine because we've got basically the same color that we got with the pure bromine earlier. All right, the next reaction is going to be potassium iodide and chlorine. So I've already filled this fifth test tube with the potassium iodide solution. So we'll add a few drops of bleach, our source of chlorine here. A couple of drops will probably be fine. 1 drop of hydrochloric acid to activate it. Ooh, looks like it's getting very colorful. And then we'll add some hexane to the top of that so we can see the color better. And now I'll just take that off for a moment just to mix it up a little bit so we can see the color a little clearer. And now you can see that lovely violet color up on the top, and that's telling us that iodine is being produced in this reaction, because it looks pretty much the same as our sample of pure iodine in the third test tube. And then our last reaction will be potassium iodide and bromine. So I've already put potassium iodide in this last test tube. So we'll add a little bit of our bromine solution to this. And then we'll mix it up. We don't have to add any hydrochloric acid to this one because the bromine is already in its pure form. So we'll take this out for just a moment. Actually, let's put the hexane in first. We'll add a little hexane to the top here so we can see it better. And now we'll take it off for just a moment and mix it up. And now, after a moment, you can see that we have that nice violet color in the last test tube as well. So the first 3 test tubes, that was our pure chlorine, pure bromine, and pure iodine. The colorless, the orange, and the violet. And then our actual reactions, we clearly formed bromine in the first reaction tube, and we formed iodine in the second tube. So that concludes all of the reactions for experiment number 9. We have the 7 reactions we did with the metals in part A and the 3 reactions with the nonmetals in part B. So go ahead and use your observations from those reactions to answer the questions at the end of the experiment, and then go ahead and submit that.